Okay, this is our first video for nuclear. So we're talking about nuclear stability and decay. So when we're talking about our unit with nuclear chemistry here, we're talking about the nucleus. Okay, we really don't care much about electrons at all in this unit. We also break a lot of rules. Okay, nuclear chemistry really is physics, so we're going to be breaking a lot of typical rules of chemistry here. Okay, so this is the only unit where you want to think about breaking some of these rules. Okay, we're not really talking about electrons, we're talking solely about the nucleus. And the biggest rule that we break here, and we do it the entire unit, is changing atoms from one element to another. And you'll see what I mean as we go on. So, first off, we need to talk about the stability of a nucleus. Okay, so unstable nuclei. Atoms with an atomic number less than 84 have at least one stable isotope except for technetium. This means they have at least one isotope, some of them have multiple, that no matter what is going to stay the same. Okay, if you just leave it alone, it will stay that element no matter what. It's just going to be stable and right. For example, carbon 12 is a stable isotope of carbon. Okay, carbon 12 has 6 protons, 6 neutrons, and it's going to stay that way. However, some elements have radioactive isotopes. And atoms with an atomic number greater than 84 are all radioactive or unstable, meaning that the nucleus is not able to stay that way because it is not stable enough. So we call it radioactive. Okay, so we have a list of radioactive isotopes on table N. Okay, you can see it starts off with gold 198. Okay, and you can see something in the middle that says half-life. We'll talk about that in another video. And decay mode, which we'll talk about in a little bit. So radioactive isotopes have nuclei that will naturally decay, meaning they're going to break apart. They cannot remain the same. Okay, they are going to change into a different element, or at least into a different isotope, I should say. Transmutation is the changing of the nucleus of one element into the nucleus of another. Okay, so that's an important vocabulary word, transmutation, changing from one element into another. So a lot of the things that we're going to be talking about today are transmutations. Okay, in fact, all of them are. Okay, so when something decays, when it's radioactive and it's unstable and it decays, it undergoes transmutation. So when we're talking about natural decay, okay, there's actually 3 different types of decay that we are going to talk about. And the first one is alpha decay. Okay, alpha decay releases an alpha particle. Over here is my alpha particle. Okay, now an alpha particle contains 2 protons and 2 neutrons. So the top part here is the mass. Okay, the bottom part is the atomic number. So the mass would be 4. The atomic number, because it contains 2 protons, would be 2. Okay. So I'm going to talk about this equation in a second, but I just want to say another way that we can write an alpha particle is the same numbers, 4 over 2, but instead we can put He because it's essentially the nucleus of a helium atom. Okay, an alpha particle is the nucleus of a helium atom. Okay, so let's look at this equation here. So here is my radioactive isotope. Uranium-238 is my radioactive isotope. Okay, so this is my unstable nucleus here. Okay, it's got 92 protons and a mass of 238. And it's going to undergo alpha decay, meaning that an alpha particle is going to come out of this nucleus. When that happens, it forms thorium-234. Why thorium-234? Well, if it's going to lose 2 protons, 2 neutrons, it's going to lose 4 mass, okay, 4 mass units, and it's going to lose 2 in the atomic number section because it loses 2 protons, right? 2 protons, 2 neutrons is an alpha particle. This arrow means yields. So this will turn into thorium-234 and the alpha particle. Okay, when uranium decays, it's going to turn into thorium-234 and the alpha particle. So there's a nice little simple way in which we can look at this. Okay, essentially, I can use this arrow here as a bit of an equal sign. Okay, and I can look at both the top and the bottom. Okay, so essentially what I'm saying here is that 234 plus 4. So 234 plus, because here's the plus, 4 equals 238. 234 plus 4, terrible plus sign, plus 4 equals 238. And the same thing down low. 92 equals 90 plus 2. 2 plus 90 equals 92. These numbers always are going to have to uh, equal up here, because if they don't, then I lost something somewhere and I can't lose anything. I'm displaying everything in my equation here. So that's alpha decay. Beta decay, excuse me, okay? Beta decay, the nucleus releases a beta particle, which changes a neutron into a proton. So when this beta particle comes out, a neutron will change into a proton. A beta particle is essentially an electron. That's why here you see it represented with an E. Okay. The other way it can be represented is a B looking thing. It's a beta symbol. Okay. It has no mass, but it has a negative charge. Okay. Very similar to an electron. In fact, it really pretty much is an electron. It just comes out of the nucleus. Now, like I said, a proton is going to be formed from a neutron. So a neutron turns into a proton. Now, protons and neutrons have the same mass, so the mass is not going to change. You can see here that iodine 131 undergoes beta decay. So iodine 131, the mass of my new element, xenon, is still going to be 131 because my beta particle has no mass. Okay, my beta particle has no mass, and a proton and neutron have the same mass. The only thing that's changing is the number of neutrons and protons. Okay, the total stays the same, but one neutron is turning into a proton. So you can see here that I actually have more protons on my right side than I do my left side. Okay, and again, if I use my little equals rule, 131 equals 131 plus 0. 53 equals 54 plus negative 1. The symbol for my beta particle is 0 over negative 1 because I'm changing a neutron into a proton. So 54 plus negative 1 is 53. Okay, here's positron decay. Now, positron decay is essentially the same as beta decay, except instead of releasing a negatively charged electron particle, it releases a positively charged beta particle that we call a positron. Okay, so again, I can have the same beta symbol here, but again, it's going to be plus 1, not minus 1. So in this case, a proton is turning into a neutron. But again, my mass is not going to change. You can see here my mass does not change because my beta particle has no mass. What does change, again, is the atomic number, and 8 equals 7 plus 1. Okay? And that is positron decay. Very similar to beta decay, except I have a positive 1 here instead of a negative 1. So of my three different types of decay here, I had alpha particles and beta particles. Okay. There's also something called gamma radiation, which can be added on to any equation. So I'm going to go back really quick. And if I were to add on, okay, if I were to add on gamma radiation to this, I'm going to erase what I drew over here. It actually doesn't affect the equation at all. All it will be is at the end, and it's going to look like a little y. Okay, and it's going to be 0 over 0, and it's the gamma symbol, which kind of looks like a y. Okay, It does not change the equation at all, but oftentimes you can see it added on at the end. So here we go, different types of radiation: alpha particles, beta particles, and gamma radiation. So alpha particles are bigger than any other type of radiation. So they don't go through very much. Okay. They're not even going to be able to make it through much of the air. Okay. So when these get released out of the nucleus, they're going to hit something pretty quickly. They're going to hit another atom. Okay. And slow down. And when they hit those other atoms, whether it be uh, the air, or if it's close enough to like a piece of paper or something like that, it's going to be stopped. Okay. Um, because of this, and because of how big it has strong ionizing ability, meaning that it's going to do some damage to whatever it hits. Beta particles are smaller. Okay, they're going to pass through the air. They're going to pass through a thin piece of paper. Okay, but they're not going to be able to pass through something that's thicker, maybe a sweatshirt, or some sort of thick fabric. Okay, they're gonna hit into something in that case. Because they're smaller, they're not going to ionize as much. They're not going to do as much damage when they hit into something. Now they can do some damage, but they're not going to do as much. Gamma radiation is a wave, like light. It's actually a form of light. It's just super high energy light. Okay, and because of its frequency and wavelength, it's going to go through almost anything. Okay, it can pass right through you. Think of like an X-ray, right? Goes through your skin, goes through your organs, but hits your bone. Gamma radiation can go through most things, including bone. Only really thick lead is going to stop gamma radiation for the most part. Okay. Now, it has no mass, no charge, it's just energy. So it's not going to affect any part of the equation like I showed you before. Okay. It's high energy and does lots and lots of damage. Okay. This is what can cause cancer and things like that when it hits like your DNA and alters your DNA. We'll talk more about that later. So table O has a list of all the different particles and their symbols, if you ever needed to go back and look at those. Okay, so that's our introduction here for nuclear chemistry. Okay, we'll be doing lots of practice with this.